All right, now we're going to talk about gases in chemical reactions. So remember, stoichiometry is just the ratio of the reactants or products in a chemical equation based on the balancing that we did. So that just comes from the coefficients. So if we were to do a reaction, for example, where we would heat a solid and a gas is formed, we might want to know if we heat up a certain number of grams of solid, how much gas would we get? And so we're going to connect the stoichiometry that we've done previously to the ideal gas law that we just covered. So the steps here, these are in your note packet. We want to figure out what we were given and what we're trying to find, all right? And then make a plan to get to the number of moles of whatever we're looking for, okay? And then we'll set up our problem and do the calculation. And then at the end, we may need to either get to mass of what we're looking for or to volume, depending on whether we were given gas or we're trying to find gas. So let's do an example. In this particular question, we have limestone, which is a solid. It reacts with hydrochloric acid, which is a solution, and makes another solution, calcium chloride, a gas, and then liquid water. Okay, so the gas that we're going to be interested in this equation is carbon dioxide. So the problem that we're given is how many liters of CO2 are produced at 752 millimeters of mercury, so that would be our pressure, and 24 degrees Celsius, that would be our temperature, from a 25 gram sample of limestone. So what we were given in this problem is 25 grams of the calcium carbonate or limestone, all right? And we're trying to find the amount of gas that we make, okay? So in order to do that, at the end, we're going to need the number of moles of CO2. So that's going to be our first goal, is to get to moles of gas, because that's, eventually what we're going to need. Okay, so if we're going to take our 25 grams of calcium carbonate, we can easily get to moles of that using our molar mass. All right, and then we can get to moles of CO2 using our balanced equation. All right, so what that's going to look like is 25 grams of calcium carbonate divided by the molar mass that we calculated from the periodic table. All right, and then this is the mole-mole ratio. In this equation, we just use one of these to make one of these, okay? It will not always be 1-to-1. It will be the ratio of your coefficients in the balanced equation. So if we were given HCl instead, there'd be a 2 down here instead of a 1. So we're going to be using our coefficients. So if we do out that math, we get 0.2498 moles of CO2. All right, so we're going to take that number and apply it to the ideal gas law. All right, so this right here is the number we just calculated in the previous step. All right, and now we need to fill in the other values we know from the balanced equation. So we have our pressure is 752. We just calculated the moles. Because our pressure is in millimeters of mercury, we're going to be using the 62.4 constant for our R value. All right, and then our temperature is 24, but we're going to need to convert that to Kelvin in order to do our calculation. So we just add 273. Okay, so now we take our ideal gas law equation. Okay, if we have 752 as our pressure, volume is what we're looking for. 0.2498 is our number of moles, 62.4 is R, our constant, and then 297 is our temperature. All right, so we multiply everything on this side, then divide by the 752 to get V alone, and we'll calculate the volume of CO2 that's produced to be 6.16 liters. All right, you could have gone the other direction. We could have been given an amount of gas and needed to calculate the number of moles to then figure out moles of something else in our balanced equation. We could also use this process to get to do a limiting reactant problem. So maybe we were given calcium carbonate and some amount of HCl, and we'd have to get to moles of CO2 for both of them in order to figure out which one would be limiting. Okay, or we could also do a percent yield kind of calculation with this. So all of the things we did with stoichiometry before, we can do now using the ideal gas law to bring gases in as well, right? The main thing is that you need to still use the mole-mole ratios from your balanced equation to get from one thing to another.